Every star you see is a messenger from the distant past. We have learned to read their stories and the story of the cosmos itself through a series of brilliant scientific triumphs. This journey will reveal how we pieced together the universe's entire history, from a fiery beginning to the formation of the atoms in your body. You will discover how a faint cosmic whisper confirmed the Big Bang, and why most of the universe is made of invisible, mysterious substances. By the end, you will understand the profound connection between human curiosity and the grand chronicle of the cosmos. How does it feel to know we can unravel mysteries billions of years old? That faint cosmic whisper is the most important map we have. It is the cosmic microwave background, the oldest light in the universe. Picture the cosmos not as a dark void, but as a faintly glowing relic, humming with the afterglow of its violent birth. This radiation is a fossil, a snapshot from when the universe was a mere 380,000 years old. Before that moment, the universe was a hot, dense fog of particles and light, too chaotic for photons to travel freely. But as it expanded and cooled, the first stable atoms formed, clearing the fog and allowing light to stream across the universe for the very first time. That first flash of light has been traveling for over 13 billion years, stretched and cooled by the expanding cosmos into the microwave whisper we detect today. Its discovery was a brilliant accident. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, mysterious static in their antenna. They pointed it at the empty sky, yet the faint hiss remained constant in every direction. They had not found a technical fault. They had found the echo of creation itself, the first solid evidence for the Big Bang. But this was only the beginning. Later missions like the COBE and Planck satellites, led by scientists like George Smoot and John Mather, mapped this afterglow with exquisite precision. They found it was not perfectly uniform. It is painted with tiny temperature fluctuations, mere millionths of a degree. These are the universe's baby pictures. These minute ripples are the seeds of everything we see today. They are the initial density differences, the slightly denser patches where gravity began its patient work, pulling matter together over billions of years to form the first galaxies, stars, and ultimately our planet. This primordial afterglow tells us not just how the universe began, but how it grew up. It leads us directly to the mysterious forces that sculpted the early cosmos, forces we are only beginning to understand. That faint cosmic whisper did more than just confirm a moment of birth. It validated a theory of breathtaking scope and precision, the Big Bang. The true power of this idea lies not in its grand narrative, but in its specific, testable predictions. It declared that if the universe exploded from an ultra-hot, ultra-dense state, then certain fingerprints must be left behind. One of these fingerprints was the exact composition of the primordial elements. The theory calculated that in the first few minutes, nuclear reactions would have fused the basic building blocks of matter, resulting in a universe made of roughly 75% hydrogen and 25% helium. When astronomers measured the oldest stars and the vast clouds of interstellar gas, that is precisely what they found. The universe's chemical foundation was laid out exactly as the theory had foretold. Another prediction was the cosmic expansion itself, first observed by Edwin Hubble as galaxies racing away from us. But the most stunning prediction was the existence of a cosmic afterglow, the cosmic microwave background, with a very specific temperature and a nearly perfect uniformity. The discovery by Penzias and Wilson was not just a lucky find. It was a checkmate. The observed radiation matched the predicted characteristics with stunning accuracy, transforming the Big Bang from a compelling idea into the established foundation of modern cosmology. This predictive power is science's greatest strength. It takes the known laws of physics and projects them backwards into the most extreme conditions imaginable, and the universe itself answers back, confirming our models. This foundational triumph gave us a reliable history of the cosmos, but it also raised profound new questions. If we now understood the universe's fiery beginning, why did its large-scale structure look the way it did? The answers would lead us to the first hints of a cosmic ingredient far stranger than anything we had yet imagined. The universe's baby pictures held a secret that its visible matter could not explain. Those tiny temperature ripples in the cosmic afterglow were the seeds for all structure, but the gravity from the atoms we know and love was simply too weak to sculpt the grand cosmic web we see today. Something else, something invisible, was doing the heavy lifting. Think of the cosmos as a grand puppet show, where the glowing stars and brilliant galaxies are the puppets we see dancing across the stage. But an unseen hand is pulling the strings, a mysterious force we call dark matter. The first hints of this puppeteer emerged nearly a century ago with a brilliant and often overlooked astronomer, Fritz Zwicky. He was studying the Coma Cluster, a vast collection of galaxies bound together by gravity. By measuring how fast these galaxies were whirling around one another, he could calculate the cluster's total mass. The result was shocking. The visible mass of all the stars and gas in those galaxies was not nearly enough to generate the gravity needed to hold the cluster together. It should have flown apart. Zwicky proposed the existence of Dunkel Materie, or dark matter, an invisible substance providing the missing gravitational glue. For decades, this was seen as a curious anomaly. Then, in the 1970s, Vera Rubin provided the definitive evidence. Her meticulous work charting the rotation speeds of stars within spiral galaxies revealed something that defied common sense. According to the laws of gravity, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly, just as Pluto orbits the Sun more slowly than Earth. But Rubin found that stars at the edge were moving just as fast as those near the center. The only explanation was that each galaxy was embedded within a massive, invisible halo of matter, a halo that extended far beyond the visible stars. This dark matter does not emit, absorb, or reflect any light. It interacts with the ordinary world only through gravity, yet it makes up about 27% of the entire mass energy content of the universe. We can map its presence indirectly through its immense gravitational influence on light itself, a phenomenon called gravitational lensing. The gravity of a massive object, like a cluster of galaxies, acts as a lens, bending and distorting the light from even more distant galaxies behind it. By studying these distorted cosmic mirages, astronomers can calculate the total mass of the foreground cluster. Time and again, the result is the same. The mass required to warp light so dramatically is far greater than the mass of all the visible stuff. A vast, unseen shadow of matter is bending the fabric of space-time. How can something so fundamental, a substance that forms the very skeleton of the cosmos, remain so completely elusive to our direct detection? The hunt for this shadowy substance, for the particles that must constitute it, continues to be one of science's greatest quests, pushing our technology to its absolute limits in deep underground laboratories and with powerful particle colliders. But the cosmic shadow of dark matter was not the final surprise. The universe had one more profound secret to reveal, a discovery so strange it redefined our ultimate fate. Think of throwing a ball into the air with all your might. You watch it rise, expecting gravity to slow its climb and pull it back down to Earth. Now imagine that instead of falling, the ball suddenly speeds up, accelerating into the sky forever. This defies everything we know, yet it is precisely what astronomers witnessed on a cosmic scale. In the late 1990s, two independent teams were using distant stellar explosions, called Type 1, a supernova, as cosmic mile markers. These supernovae are special. They all explode with roughly the same intrinsic brightness, which means by measuring how bright they appear from Earth, we can calculate their precise distance. By looking at these standard candles billions of light years away, the astronomers were effectively looking back in time, measuring how fast the universe was expanding in its youth. They expected to see the expansion slowing down, gradually braked by the collective gravitational pull of all the matter in the cosmos. What they found was the opposite. The most distant supernovae were fainter than they should have been. They were farther away than any model of a slowing universe could explain. The only possible conclusion was staggering. The expansion of the universe is not slowing down, it is speeding up. Something is overpowering the relentless pull of gravity, pushing galaxies apart at an ever-increasing rate. This mysterious, repulsive force was named dark energy. It is not a substance like dark matter, but rather a property of space itself. Empty space, according to this idea, is not nothing. It possesses a latent energy that causes the very fabric of the cosmos to stretch at an accelerating pace. This single discovery turned cosmology on its head. We now understand the cosmic budget in humbling terms. The ordinary atoms that make up every star, planet, and person account for a mere 5% of the universe. Dark matter, the invisible skeleton, makes up about 27%. The remaining 68%, the dominant force controlling the destiny of everything, is dark energy. This enigmatic pressure sealed the universe's fate, pointing toward a future of endless expansion, a gradual cooling, and a final state of cosmic isolation. But what is it? Is it a cosmological constant, an innate energy of the vacuum as Einstein once briefly proposed? Or is it something even more exotic, a dynamic field that could change over time? Unraveling the nature of dark energy forces us to confront the deepest questions at the frontier of theoretical physics, questions about the fundamental nature of reality. That remarkable discovery of dark energy revealed the fate of the cosmos, but it was an earlier triumph that uncovered our own cosmic origin. The iron in your blood and the calcium in your bones were not present at the universe's birth. They were forged much later in the hearts of stars that lived and died long before our sun was born. We are literally made of stardust, and the theory that explains this beautiful connection is called stellar nucleosynthesis. It is the story of how stars became the universe's great alchemists. This grand idea was championed by the brilliant and often controversial astronomer Fred Hoyle. He and others realized that stars are not just distant points of light. They are immense, self-regulating nuclear furnaces, deep within their searing cores, under crushing pressures and temperatures of millions of degrees. The fundamental process of nuclear fusion occurs. A star like our Sun spends most of its life fusing the primordial hydrogen from the Big Bang into helium. This steady release of energy is what makes a star shine. For most stars, this is where the story ends, but for the most massive stars, a far more dramatic and creative sequence unfolds. As a massive star runs out of hydrogen fuel, its core contracts and grows even hotter. This ignites the next stage of fusion, forcing helium atoms to fuse into carbon. Then, carbon fuses into oxygen, and so on, building progressively heavier elements like neon, magnesium, and silicon in concentric shells, like the layers of a cosmic onion. The star's core becomes a factory, relentlessly climbing the periodic table. But this factory has a hard stop. The process of fusion releases energy only up to the element iron. Fusing iron into anything heavier actually consumes energy. At that moment, the star's energy source vanishes. Without the outward pressure from fusion to counter its own immense gravity, the star collapses catastrophically in a fraction of a second, then rebounds in one of the most violent events in the universe, a supernova explosion. The energy of that blast is so unimaginably intense that it forges all the elements heavier than iron, like gold, silver, and uranium, and then hurls them, along with all the other newly forged elements, out into the galactic void. More recently, we have learned that the very heaviest elements can also be created in the collisions of neutron stars, another cataclysmic event that seeds the cosmos with precious matter. This entire cycle explains the cosmic abundance of every element we find. It tells us why the universe is rich in carbon and oxygen, the building blocks of life, and why gold is so rare, forged only in the most extreme and fleeting events. How did scientists piece together this cosmic genealogy of matter? The proof is not just in our telescopes, but in our very bodies. Every time you take a breath, you are inhaling oxygen that was created in a long-dead star. The ring on your finger contains gold forged in a stellar cataclysm that occurred billions of years ago. This stellar alchemy did more than just create the periodic table. It set the stage for the next great cosmic achievement, the formation of planets capable of hosting complex chemistry and, ultimately, life itself. Our own galaxy, the Milky Way, is just one member of a vast cosmic zoo. For centuries, astronomers saw these faint, fuzzy patches in the sky as simple nebulae. It was only when we understood their true nature as immense islands of stars that a new challenge emerged: how to make sense of their staggering diversity. This was the task Edwin Hubble undertook, acting as a cosmic zoologist tasked with classifying the universe's most magnificent creatures. He brought order to the chaos with an elegant and enduring system, the Hubble sequence, often visualized as a tuning fork. At the handle of the fork lie the elliptical galaxies, smooth and featureless spheres or ovals of stars, ranging from nearly round to highly elongated. Branching out from the handle are the two prongs of the fork. One prong holds the majestic spiral galaxies like our own Milky Way, with their bright central bulges and sweeping, pinwheeling arms. The other prong contains the barred spirals, similar to the pure spirals but with a prominent straight bar of stars cutting through their center. And then there are the irregulars, the galaxies that defy this neat classification, often misshapen by violent gravitational encounters. This was far more than just cosmic stamp collecting. Hubble's classification became a Rosetta Stone for galactic life stories. The shape of a galaxy is a direct window into its history and its future. Spiral galaxies, with their blue-tinged star-forming arms, are cosmic nurseries, vibrant and active. They are rich with the gas and dust needed to birth new generations of stars. Their very structure suggests a dynamic, ongoing evolution. In stark contrast, the elliptical galaxies appear smooth, red, and ancient. They are dominated by older, redder stars and contain very little free gas for new star formation. They are the cosmic retirement communities, vast collections of aging stars that have largely settled into a quiet, static existence. The tuning fork diagram itself seemed to suggest an evolutionary path, perhaps from a dynamic spiral to a quiescent elliptical. The true story, however, is far more dramatic. We now understand that the primary force shaping these galactic forms is not a gentle transition, but cosmic violence. Giant elliptical galaxies are not simply aged spirals. They are most often the products of titanic collisions, the mergers of two or more spiral galaxies. When these immense structures smash together, their delicate spiral arms are shredded, and their gas is either consumed in a firestorm of new star formation or violently ejected. The resulting galaxy is a smooth, blended ellipsoid, a fossil record of a catastrophic past. Even the beautiful spirals are shaped by interactions, with smaller satellite galaxies influencing the structure of their arms. What do these galactic shapes tell us about the violent history of the universe? They reveal a cosmos in constant gravitational turmoil, where the majestic structures we admire are the scars and trophies from eons of cosmic battles. Building a universe from scratch is no longer a fantasy. Inside the world's most powerful supercomputers, we are doing exactly that, creating entire digital cosmos that unfold over billions of simulated years. These are not simple animations, they are complex virtual laboratories governed by the strict laws of physics, starting with the same primordial ripples we see in the cosmic microwave background, and then letting gravity, dark matter, and gas dynamics take over. The goal is breathtakingly ambitious: to watch cosmic history play out from the first dark matter halos to the majestic galaxies we see today, all within a supercomputer's memory. One of the most famous of these projects was the Millennium Simulation, a landmark endeavor that used more than 10 billion virtual particles to trace the evolution of dark matter across a vast volume of space. The simulation revealed a cosmic web of stunning complexity, with dark matter forming a delicate filamentary structure, a scaffolding upon which galaxies would later be built. But that was just the skeleton. Modern simulations go much further, incorporating the messy physics of ordinary matter, the gas that cools and collapses to form stars, and the violent feedback from supernovae and black holes that can heat surrounding gas or blow it entirely out of a galaxy, shutting down star formation. Watching a simulation run is like having a time machine for the cosmos. You can witness two spiral galaxies, each with billions of stars, slowly drawn together by gravity, their structures warping and twisting until they merge into a single, giant elliptical galaxy, a process that takes billions of years in reality but mere hours inside the machine. This virtual reality directly addresses one of astronomy's long-standing puzzles: why the observed distribution and shapes of galaxies match the predictions of our cosmological models so well. The simulations show us that the initial seeds from the Big Bang, when combined with the gravitational influence of dark matter and the complex behavior of gas, naturally give rise to the cosmic zoo of galaxies we catalogue. They act as a crucial bridge between theory and observation. When a simulation produces a universe that looks like our own, it gives us profound confidence that we are on the right track. When it does not, it points to a missing piece of physics, a clue that our understanding of star formation or black hole growth is incomplete. These digital universes have become indispensable, the testing grounds for our next great leaps into the unknown, allowing us to experiment with the fundamental rules of reality itself. Measuring the distance to a star is one of the most fundamental and difficult challenges in all of science. We cannot stretch a tape measure across the void, and for the farthest galaxies, even a powerful telescope shows only a faint smudge of light. To solve this, astronomers constructed a brilliant step-by-step tool known as the Cosmic Distance Ladder. Think of it as a series of interlocking measurement techniques, where each rung provides a solid foundation to reach for the next. The first rung is built on simple geometry, using the tiny apparent shift in a star's position, called parallax, as Earth orbits the Sun. It is the same effect you see when you hold a finger up and close one eye, then the other, watching your finger appear to jump back and forth against the background. For stars, this shift is minuscule, but it gives us a direct geometric measurement for our celestial neighborhood. This foundational step is crucial because it calibrates the next rung of the ladder, which relies on stars whose true brightness we can deduce. These are the standard candles. A classic example is the Cepheid variable star, a type of star that pulses rhythmically, and the period of its pulse is directly related to its intrinsic brightness. By knowing how bright it truly is and comparing that to how dim it appears from Earth, astronomers can calculate its distance with great precision. Cepheids are bright enough to be seen in relatively nearby galaxies, allowing us to measure distances far beyond the reach of parallax. This is where the ladder truly extends its reach. The most powerful standard candles are the Type 1, a supernova, the very same stellar explosions that revealed the accelerating universe. Because these supernovae all explode with nearly the same peak brightness, they act as brilliant cosmic beacons visible across billions of light years. By carefully observing them in galaxies whose distances were already known from Cepheid variables, astronomers could confirm their standard candle status. This painstaking cross-checking, this careful calibration of one rung against the next, is what gives the entire ladder its strength. For the most remote objects where individual stars cannot be resolved, the ladder uses the stretching of light itself. As the universe expands, it stretches the wavelength of light from distant galaxies, shifting it toward the red end of the spectrum. By measuring this redshift, and by knowing the relationship between redshift and distance established by the lower rungs of the ladder, we can gauge the vast distances to the earliest galaxies. How do we trust a measurement that spans the entire visible universe? The answer lies in the meticulous overlap of every technique. Each method has its own domain of reliability and its own potential for error, but by building them one upon the other and checking them against each other, scientists achieve a remarkable consensus. This entire intricate structure was absolutely essential for determining the Hubble constant, the rate of the universe's expansion, and for making the shocking discovery that this rate is increasing. Every story we tell about the cosmos, from its birth in the Big Bang to its fate driven by dark energy, rests upon the unwavering certainty of this carefully constructed ladder, a testament to our ingenuity in measuring the immeasurable. Gravity does more than just hold us to the ground. It sculpts the light of the cosmos. Einstein's theory of general relativity revealed that massive objects warp the fabric of spacetime, and light, traveling through that warped space, does not travel in a straight line. It bends. This prediction, once a revolutionary idea, is now a cornerstone of modern astronomy, a phenomenon we call gravitational lensing. Think of it as the universe's own natural telescope. When a massive object like a galaxy cluster sits directly between us and a more distant galaxy, its immense gravity acts like a giant lens. It can distort that background galaxy's light into spectacular arcs, or even a perfect circle of light known as an Einstein ring. This is strong lensing, a dramatic cosmic mirage, but there is also a more subtle version. Weak lensing does not create rings or arcs. Instead, the gravity of vast, unseen structures subtly shears the shapes of millions of distant galaxies, stretching them in a coherent direction. By meticulously measuring these tiny, statistical distortions, astronomers can map the invisible scaffolding of dark matter that permeates the cosmos. The true power of this natural telescope lies in its ability to see the unseen. We cannot detect dark matter directly, but we can watch how its gravity bends light, allowing us to chart its distribution with incredible precision. Furthermore, this lensing effect magnifies the light of incredibly distant galaxies, bringing into view infant galaxies so far away they would otherwise be nothing more than faint smudges. Massive galaxy clusters become our ultimate magnifying glasses, amplifying the light from the early universe and revealing details of galactic birth that were once beyond our reach. What has this cosmic lens shown us? It has unveiled some of the most distant galaxies ever observed, giving us a direct glimpse into the era when the first galaxies were assembling. It provides independent, overwhelming evidence for the cosmic web of dark matter, confirming the large-scale structure we see in our supercomputer simulations. Every warped image and stretched galaxy is a direct measurement of mass, a testament to the fact that the cosmos is filled with far more than meets the eye. That cosmic distance ladder gives us the precise location of stars, but how do we understand their lives? A single graph, elegantly simple in its design, holds the entire story of stellar evolution. The Hertzsprung-Russell Diagram is a map of the stars, charting their temperature against their luminosity. When you plot hundreds of thousands of stars on this graph, a stunning pattern emerges. Most of them fall along a smooth, diagonal band that astronomers call the main sequence. This is where stars, including our own Sun, spend the prime of their lives, steadily fusing hydrogen into helium in their cores. A star's position on this main sequence is not random. It is determined almost exclusively by its mass. Hot, brilliant blue stars are the massive, short-lived titans, burning through their fuel with ferocious speed. Cooler, dimmer, red stars are the lightweight, frugal ones, destined to shine for trillions of years. But the diagram's true power lies in the regions outside the main sequence. Look to the upper right, and you will find the red giants and supergiants. These are stars that have exhausted the hydrogen fuel in their cores. Their inner furnaces have reconfigured, causing their outer layers to expand to monstrous sizes while their surfaces cool, turning red. In the lower left, a completely different family resides, the white dwarfs. These are the exposed, incredibly dense cores of dead stars, no longer generating fusion energy, slowly cooling into cosmic cinders over eons. By simply measuring a star's color and its true brightness, an astronomer can place it on this diagram and instantly read its life story, its current age, and its ultimate fate. A star's mass dictates its journey. A star like our Sun will one day leave the main sequence, swell into a red giant that may engulf the inner planets, then eventually shed its outer layers and leave behind a white dwarf. A star many times more massive than the Sun will race through its life and end in a spectacular supernova, its core collapsing into a neutron star or even a black hole. This single plot transforms a random scatter of points of light into a coherent narrative of cosmic life and death. It tells us that the brilliant, familiar pinpoints in our night sky are not permanent. They are each at a different point in a grand, dynamic cycle, a cycle that forges the elements and seeds the galaxy with the raw materials for new stars, planets, and life itself. The smooth uniformity of the cosmic microwave background presented a profound mystery. How could regions of the universe on opposite sides of the sky, regions that could not have possibly exchanged light or information since the beginning, have the exact same temperature? This was the horizon problem, a cosmic conundrum that threatened to unravel our understanding of the Big Bang. Furthermore, the universe's geometry appeared perfectly balanced or flat, teetering on a knife's edge between eternal expansion and catastrophic collapse. This was the flatness problem. The solution to both required a radical new idea, a brief but monumental growth spurt in the universe's infancy known as cosmic inflation. Proposed by physicist Alan Guth, inflation suggests that a fraction of a second after the moment of creation, the universe was seized by a repulsive force, likely driven by a strange energy field. This force caused space itself to expand at an exponential rate, far surpassing the speed of light for a fleeting instant. This was not matter moving through space faster than light, which is impossible, but the fabric of space-time itself stretching at an unimaginable pace. In less time than it takes to blink, a subatomic speck of space was blown up to a size larger than our entire observable universe today. This hyper-expansion elegantly solved the horizon problem. Before inflation, that tiny patch was small enough for every part to be in contact, allowing it to reach a uniform temperature. Inflation then simply stretched this smooth, homogeneous region into the vast cosmos we see, explaining why the background glow is the same in every direction. It also solved the flatness problem. Imagine taking a tiny, wrinkled crinkle from a piece of paper and inflating it into a gigantic, perfectly smooth balloon. No matter how curved that initial crinkle was, after such immense stretching, any curvature would be smoothed away to near perfection. Our universe appears flat for the same reason, stretched smooth by its explosive infancy. But inflation did more than just solve puzzles. It also created the seeds for all future structure. At the quantum level, tiny fluctuations were inevitable. Inflation magnified these microscopic ripples to cosmic proportions, stretching them into the slight density variations that would later, under the relentless pull of gravity, collapse to form the first galaxies. The pattern of hot and cold spots we see in the cosmic microwave background is the direct imprint of these quantum seeds, a prediction of inflation that has been stunningly confirmed. What could have possibly triggered such a brief, violent event, and what caused it to stop? The answers to these questions lie at the very frontier of physics, in realms of energy where our current theories break down. The legacy of this fleeting epoch, however, is written across the sky, in the large-scale structure of the universe and the very fact that we are here to observe it. The search for other worlds was once the domain of fantasy, but it is now a rigorous scientific discipline that has utterly transformed our cosmic perspective. For centuries, we could only wonder if other stars hosted their own families of planets. That profound question was answered definitively in 1995, with the discovery of the first planet orbiting a Sun-like star, 51 Pegasi b. This was not a terrestrial world like our own, but a giant gas ball orbiting perilously close to its star, a type of planet that defied all our expectations. It proved that other solar systems could be wildly different from our own. This single discovery opened the cosmic floodgates. Dedicated space telescopes, like the Kepler mission, stared unblinkingly at a single patch of sky containing over 100,000 stars. Its mission was simple yet profound: to look for the telltale, repetitive dimming that occurs when a planet crosses or transits the face of its host star. This transit method revealed a universe teeming with planets. Kepler alone confirmed thousands of worlds, and its successor, TESS, is now scanning nearly the entire sky. The statistical conclusion is inescapable: planets are not rare. There are more planets in our galaxy than there are stars. We live in a cosmos rich with untold billions of worlds. Another crucial technique, the radial velocity method, measures the subtle wobble of a star. A planet's gravity does not just keep the world in orbit, it also tugs on the star itself, causing it to move in a tiny, rhythmic dance. By measuring the star's shifting light, astronomers can deduce the planet's mass and orbit. These two techniques together have built our first crude census of the galactic population. But finding a planet is only the first step. The next, more profound question is whether any of these distant worlds could be habitable. This is where the concept of the habitable zone becomes central. Often called the Goldilocks zone, it is the orbital region around a star where the temperature is just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. Water, as far as we know, is the essential solvent for life. A planet residing in this zone possesses the most basic prerequisite for biology as we understand it. But location is not everything. A small, rocky planet like Mars may sit in the Sun's habitable zone yet be unable to retain a thick atmosphere, while a large, gaseous world like Venus with a runaway greenhouse effect becomes a scorching hellscape. The true characterization of these worlds is the new frontier. The most powerful tool for this is spectroscopy. When a planet transits its star, a tiny fraction of the star's light filters through the planet's atmosphere. Different gases in that atmosphere absorb specific wavelengths of light, leaving behind a unique chemical fingerprint. By analyzing this starlight, we can read the composition of an alien atmosphere from light years away. The ultimate goal is to search for biosignatures, combinations of gases that are difficult to explain without biological activity. On Earth, the persistent coexistence of oxygen and methane in our atmosphere is a powerful signature of life, as these gases quickly react with each other and must be continuously replenished. Detecting a similar imbalance on a distant exoplanet would be a monumental discovery. We are now building telescopes with this explicit purpose, to analyze the light from Earth-sized worlds in habitable zones and search for these signs. This ongoing search forces us to confront one of humanity's oldest questions. Are we a singular accident, or is our galaxy a vast garden of worlds, some of which may be looking back at us, wondering the very same thing? For centuries, our view of the cosmos was limited to a single sense, sight. We were deaf to the universe's symphony. That changed with the dawn of multi-messenger astronomy, an era where we now observe the cosmos through multiple cosmic messengers simultaneously. This new approach allows us to hear the universe as well as see it. The landmark event occurred in August of 2017. Observatories around the world detected the ripples in spacetime from two neutron stars colliding, a signal picked up by the LIGO and Virgo gravitational wave detectors. Just 2 seconds later, orbiting telescopes caught a powerful flash of gamma rays from the same patch of sky. For the first time, we had both heard the crash and seen the flash of a cosmic catastrophe. This was not just a confirmation of Einstein's predictions, it was a new form of cosmic triangulation. The gravitational waves pinpointed the general region of the event, and the subsequent flood of light across every wavelength, from X-rays to radio waves, allowed telescopes to zoom in and identify the host galaxy. That flash of light was more than just a beacon, it was a cosmic alchemist's forge in action. The intense conditions of the merger forged a cloud of heavy elements, including vast amounts of gold and platinum. In that one event, we witnessed the origin of the precious metals in our jewelry, proving that the universe's most valuable elements are created in these violent stellar collisions. But the scientific payoff did not stop there. By comparing the strength of the gravitational waves with the observed brightness of the explosion, astronomers could independently measure the Hubble constant, the rate of the universe's expansion. This provided a crucial cross-check on other methods, helping to resolve a growing tension in cosmology. This single event, observed through multiple cosmic senses, solved mysteries of elemental origins and cosmic expansion all at once. It demonstrated that the most powerful events in the universe broadcast their stories on multiple channels. We are no longer passive observers of a silent movie. We are now tuning into a full sensory experience, listening to the gravitational hum of black holes, feeling the ghostly passage of neutrinos from the sun's core, and tracing the paths of high-energy cosmic rays. Each messenger carries a unique piece of the puzzle. Gravitational waves tell us about the dynamics of massive objects warping space-time, while light reveals the composition and temperature of cosmic matter. By combining them, we get a complete, multi-sensory picture of the universe's most extreme phenomena. What other cosmic broadcasts are we now equipped to receive? This collaborative method is our most powerful tool for cracking open the universe's most impenetrable mysteries, from the inner workings of supernova to the dark hearts of active galaxies. This vast cosmic web is not a static sculpture. It is a dynamic, flowing river of matter on the grandest possible scale. The great filaments act as cosmic highways, channeling vast flows of gas from the empty voids toward the dense intersections, the galaxy clusters and groups. This continuous supply of fresh hydrogen fuel is the lifeblood for star formation. A galaxy's position within this web directly controls its destiny. A galaxy living in a dense cluster at a busy intersection of filaments is a galaxy under constant gravitational stress. It experiences frequent, violent encounters with its neighbors, which can strip away its gas, disrupt its elegant spiral structure, and effectively starve it, halting the birth of new stars. This is why the giant elliptical galaxies we find at the hearts of clusters are often red and dead, their star-forming fuel depleted by the harsh cluster environment. In contrast, a galaxy residing in a quieter, smaller filament or in a more isolated region can lead a more peaceful existence. It can hold onto its gas, maintaining a steady, sustained rate of star formation and often preserving its beautiful spiral shape for billions of years. The cosmic web is the ultimate architect, sketching the blueprints for galactic life. The immense effort to map this structure, like the Sloan Digital Sky Survey, involved systematically measuring the redshifts of millions of galaxies, painstakingly building a three-dimensional atlas of the cosmos. The resulting map is breathtaking, a confirmation of our deepest cosmological theories. It shows a universe exactly as our models predicted. A frothy, bubble-like structure where galaxies trace out the underlying, invisible skeleton of dark matter. Those tiny quantum ripples from the universe's first moments, stretched by inflation and then amplified by gravity, have grown into this magnificent, interconnected celestial city. How does this cosmic metropolis continue to evolve? The web itself is still growing, its filaments tightening and its voids emptying out as gravity continues its patient work. The next generation of telescopes will map this structure in even greater detail, tracing the faint glow of intergalactic hydrogen within the filaments themselves, allowing us to watch this cosmic river system in real time and understand the complete journey of matter from the primordial dawn to the vibrant galaxies we see today. The very existence of stars, planets, and us hinges on a single, staggering cosmic imbalance. Our most fundamental theories tell us the Big Bang should have produced a perfect symmetry, equal amounts of matter and antimatter. For every particle of matter born, a mirror particle of antimatter should have emerged. These opposites, upon meeting, would have annihilated each other in a flash of pure energy, leaving behind a cold, empty, and lifeless cosmos. The fact that we are here in a universe teeming with material substance means this perfect symmetry was broken. A tiny, 1 in a billion preference for matter over antimatter must have occurred in the universe's first fleeting moments. This is the mystery of baryon asymmetry, and it asks the most profound question of all: why is there something instead of nothing? The physicist Andrei Sakharov outlined the 3 essential conditions needed to create this imbalance from an initially symmetric state. First, the universe needed to be out of thermal equilibrium, a condition easily satisfied by its rapid, explosive expansion. Second, there needed to be processes that violated a fundamental symmetry known as charge conjugation and parity, or CP. In simple terms, this means the laws of physics must treat matter and antimatter not as perfect mirror images, but must slightly favor one over the other. Third, these processes had to violate baryon number, meaning they could change the total amount of matter in the universe. we have observed CP violation in the delicate behavior of certain subatomic particles like kaons and B mesons in laboratory experiments. But the effect is far too small to account for the vast abundance of matter we see today. The hunt is now on for new, more powerful sources of this symmetry breaking, a search that takes us to the frontiers of both theory and experiment. Inside colossal machines like the Large Hadron Collider, physicists are smashing particles together at nearly the speed of light, recreating the conditions of the early universe. They are meticulously comparing the decay rates of particles and their antiparticle counterparts, looking for any tiny discrepancy, any faint whisper of a preference that could explain our material existence. What hidden particle or unknown force intervened in that first fraction of a second to tip the scales? The answer lies in physics beyond our current standard model, in realms we have only begun to probe. Solving this puzzle is not just about completing a theoretical equation. It is about understanding the most fundamental reason for our own being. This new eye on the sky is already rewriting the first chapters of our cosmic story. The James Webb Space Telescope acts as a time machine, its giant gold-coated mirror and infrared sight focused on the era of first light. Launched in 2021, it was designed to peer through veils of cosmic dust and witness the birth of the very first stars and galaxies, a period we call the Cosmic Dawn. While the Hubble Space Telescope showed us a universe of mature galaxies, James Webb was built to see their infancy. Its infrared vision is crucial because the light from the most distant, ancient objects has been stretched by the expansion of the universe. What began as visible light has been shifted into the infrared part of the spectrum, and Webb is uniquely equipped to catch these long, red waves. It sees the glow of cosmic nursery clouds where stars are being born, and it can analyze the atmospheres of distant exoplanets, searching for the chemical fingerprints of water vapor, methane, and carbon dioxide. But its most startling discoveries have come from looking back to the very edge of observable time. Early observations revealed galaxies that were shockingly massive and fully formed, existing when the universe was only a few 100 million years old. This is a profound puzzle. According to our existing models, there simply should not have been enough time for gravity to pull together so much matter and fashion it into such mature, structured galaxies so quickly. These cosmic toddlers are far too advanced for their age, forcing astronomers to reconsider the entire timeline of how structure emerged from the primordial darkness. Was the early universe seeded with more clumps of dark matter than we thought? Did the first stars form with unbelievable efficiency? Each new image from Webb is a data point from the frontier, a direct glimpse into an epoch we could previously only simulate. How will this flood of new evidence reshape our fundamental narrative of galactic birth? The universe's childhood album is being filled with pictures that are both breathtaking and deeply challenging, proving that our cosmic history is far from a settled book. Our farthest spacecraft carry secrets in their silent flight. The Pioneer and Voyager probes, now billions of miles from home, have experienced forces that defy simple explanation. For the Pioneer spacecraft, the mystery was a persistent, tiny deceleration. As they journeyed toward interstellar space, a slight but constant extra force was acting upon them, a gentle, unseen brake that pulled them back toward the sun. This was the Pioneer anomaly, a deviation so small it was like measuring a single extra grain of sand added to a beach, yet it persisted for decades. The precision of their navigation was so high that this minuscule drift stood out, a ghost in the machine of celestial mechanics. Scientists explored every possibility, from the gentle push of heat radiating from the spacecraft's own electronics and nuclear power source to the radical idea that our understanding of gravity itself might be incomplete in the vast, weak gravity expanse of the outer solar system. After years of painstaking analysis, the most likely culprit turned out to be the spacecraft itself, a subtle and complex effect of thermal radiation pressure. The probe's plutonium power source generated heat, and that heat, radiating off the vessel's structure, provided just enough thrust to create the observed slowdown. This case was a stunning demonstration of measurement science, where tracking a spacecraft became a test of fundamental physics. The Voyager probes have revealed a different kind of puzzle at the solar system's edge. They are our first scouts to directly sample the heliosphere, the vast protective bubble of particles and magnetic fields blown by the solar wind. As they crossed the turbulent boundary where this bubble meets the interstellar medium, the data was full of surprises. The region was far more complex and dynamic than anyone had predicted, with magnetic fields piling up like traffic jams and a froth of energized particles at the frontier. These missions continue to act as long-distance laboratories, their faint signals testing our models of space itself. What other subtle forces, hidden in the quiet darkness between the stars, are waiting to be discovered by these silent travelers? The profound silence of the cosmos carries a disturbing question. If the universe is so vast and ancient with countless stars and planets, why does it seem so empty of other voices? The physicist Enrico Fermi famously captured this paradox with a simple, devastating query. Where is everybody? Decades of searching for extraterrestrial intelligence have yielded only silence, a great quiet that challenges our place in the cosmos. One compelling answer to this puzzle is the Great Filter hypothesis. This idea suggests that the path from non-life to a spacefaring civilization is not a smooth highway, but a treacherous obstacle course. Somewhere along that journey, from the first stirrings of chemistry to the mastery of interstellar travel, there exists a barrier so formidable that almost every potential civilization fails to cross it. This filter could lie in our past. Perhaps the origin of life itself was an astronomically rare event, a chemical lottery that we just happened to win. Or maybe the critical jump from simple prokaryotic cells to complex eukaryotic cells, the foundation of all multicellular life, was a 1 in a billion fluke that took billions of years to occur on Earth. If the filter is behind us, it means we are inconceivably lucky, the sole winners of a cosmic lottery. But the more unsettling possibility is that the great filter awaits us in the future. Perhaps the development of advanced technology inevitably leads to a civilization's self-destruction, whether through nuclear war, engineered pandemics, or an environmental collapse triggered by its own success. The silence we hear could be the ghostly echo of countless other civilizations that reached our level of development only to vanish. The scientific triumph here is turning a philosophical wonder into a framework for testable, probabilistic reasoning. As we discover more about the conditions for life and the history of our own planet, we can assign rough odds to each potential filter. Finding fossil evidence of life on Mars, for instance, would be thrilling, but it would also be deeply worrying. If life arose independently on two different worlds in our own solar system, it would suggest that the beginning of life is not the great filter. That would make it far more likely that the filter, the thing that silences civilizations, still lies ahead of us. This paradox forces a humbling self-reflection. Our own technological adolescence, with all its promise and peril, might be the most dangerous phase any intelligent species ever faces. Does the universal quiet contain a warning for humanity, a lesson we must learn from the silence of others? The quiet frontier of our solar system hides a vast frozen realm. For decades, we pictured Pluto as a lonely, distant world, a singular oddball at the system's edge. This view was completely overturned in the 1990s with the discovery of the Kuiper belt, a colossal reservoir of icy bodies orbiting the Sun beyond Neptune. Astronomers suddenly realized that Pluto was not alone. It was simply one of the largest and first discovered members of an entirely new class of solar system objects. This was not just the discovery of a few new rocks, it was the discovery of a whole new zone of our cosmic neighborhood, a third region after the terrestrial and gas giant planets. The architecture of our solar system had to be completely redrawn. This new understanding forced a difficult but necessary scientific conversation. If Pluto is a planet, then what about the other large Kuiper belt objects being discovered, like Eris, which was initially thought to be even more massive than Pluto? The astronomical community faced a choice to have a solar system with dozens and potentially hundreds of planets, or to refine the definition of what a planet truly is. In 2006, the International Astronomical Union made a historic decision. They established 3 criteria for a full-fledged planet. It must orbit the Sun, it must be massive enough for its own gravity to pull it into a nearly round shape, and it must have cleared the neighborhood around its orbit. Pluto meets the first 2 criteria, but it fails the third. Its orbital path is populated with countless other Kuiper belt objects. It has not dominated its gravitational environment. This led to its reclassification as a dwarf planet, a move that sparked intense public debate but reflected a more precise and meaningful scientific categorization. The emotional attachment to Pluto was understandable, but science must move forward with clarity. The ultimate vindication for Pluto's importance came not from its planetary status, but from our first close-up look. The New Horizons mission's flyby in 2015 revealed a world of breathtaking complexity. We did not see a dead, cratered ball of ice. Instead, we found towering mountains of water ice, vast, smooth plains of solid nitrogen glaciers, and evidence of a subsurface ocean. That iconic heart-shaped feature on its surface, named Tombaugh Regio, is a massive glacier of frozen nitrogen that is slowly flowing, constantly renewing the landscape. Pluto is a dynamic, active world. This single mission transformed our view of these distant, frozen bodies from inert relics into geologically active worlds. So how does the study of this frozen archive inform our models? The Kuiper belt is a deep freeze, preserving the original building blocks of the solar system in a near-pristine state. By studying the composition and orbits of these icy bodies, we are reading a fossil record of the solar system's formation. They are the leftover planetesimals that never coalesced into a larger planet, held in a gravitational stasis by Neptune's influence. Their very existence and distribution provide a critical test for our models of how the giant planets migrated in the solar system's youth, scattering these icy fragments into their current orbits. Every dwarf planet and every icy chunk in this distant belt is a time capsule, holding clues to the chaotic processes that built our planetary home. A flash of cosmic power defies all intuition. In the span of a single millisecond, a fast radio burst can unleash more energy than our Sun will emit over 80 long years, a titanic roar from across the universe. These FRBs are not the steady signals of pulsars or the predictable light of variable stars. They are cosmic lightning strikes, brief and overwhelmingly powerful, their origins hidden in galaxies billions of light years away. Since the first one was spotted by accident in 2007, astronomers have catalogued hundreds of these events, each one a new piece of a profound puzzle. Most are loners erupting once and then vanishing back into silence. A precious few, however, are repeaters, flaring up again and again from the same patch of sky, but with no discernible pattern. This erratic behavior is a crucial clue, pointing toward a source that can survive its own cataclysm. What kind of cosmic object can explode with such ferocity, over and over, without being utterly destroyed? Prime suspects are some of the universe's most extreme objects. Highly magnetized neutron stars, known as magnetars, possess magnetic fields so intense they could strip the information from a credit card from 500,000 miles away. A starquake on such an object, a sudden cracking of its rigid crust, could potentially unleash a flash of radio waves that would be visible across the cosmos. Other theories point to the violent mergers of neutron stars or even exotic physics around newly formed black holes. The real breakthrough in unraveling this mystery has not come from understanding the source itself, but from an incredible feat of cosmic triangulation. By using vast arrays of radio telescopes spread across continents, astronomers have managed to pinpoint the location of several FRBs, tracing them back to their specific host galaxies. This is a monumental achievement. It transforms a mysterious blip of energy into an event with an address, a context, and this localization has yielded a surprising bonus. As these powerful radio waves race across the universe, they pass through the diffuse clouds of ionized gas that float in the vast emptiness between galaxies. This material, nearly impossible to detect by any other means, subtly distorts the radio signal, slowing different wavelengths by different amounts. By analyzing the precise fingerprint of this distortion, scientists can literally weigh the missing atoms in the cosmic voids, using the FRB as a backlight to illuminate the invisible scaffolding of the universe. So what ultimate physical extremes are we witnessing? Cracking the code of fast radio bursts will open a window into environments where matter is stretched to its absolute limits, governed by laws of physics we can only begin to imagine. Our galaxy is revealing its biography through the subtle motions of 1 billion stars. The European Space Agency's Gaia mission is an unprecedented astronomical observatory, dedicated not to taking pretty pictures, but to the meticulous work of celestial cartography. Its goal is to construct the largest and most precise three-dimensional map of our Milky Way ever made. It achieves this by repeatedly scanning the sky, measuring the positions, distances, and velocities of over 1 billion stars with staggering accuracy. For some stars, Gaia's measurements are so precise they are equivalent to pinpointing the diameter of a human hair from 1,000 miles away. This river of data is transforming our static, two-dimensional view of the galaxy into a dynamic, rotating cosmic metropolis. We are no longer just looking at a snapshot, we are watching a movie of our galactic home. This vast census allows for a new science called galactic archaeology, where we trace the motions of stars backward in time to uncover our galaxy's violent history. One of its most stunning discoveries is the ghost of a long-dead galaxy named Gaia Enceladus. Billions of years ago, this smaller galaxy collided with and was consumed by the infant Milky Way. The stars from that cataclysmic merger were not lost, they were simply mixed into our galaxy's halo. Gaia identified them by their distinct, looping orbits, a celestial fossil record of a primordial collision that helped shape the galaxy we see today. But Gaia's revelations do not stop with ancient history. By watching for the telltale wobble in a star's position, it has discovered thousands of new exoplanet candidates. It has catalogued failed stars known as brown dwarfs and has even tracked near-Earth asteroids with incredible precision, all as a byproduct of its primary stellar mission. How will this continuous, precise tracking of 1 billion points of light rewrite our galactic story? We are witnessing the dawn of a new era in astronomy, where our map of the Milky Way is no longer a static drawing, but a living, breathing entity with a memory of its own turbulent past. Gravity is not a mysterious force reaching across space. but the very shape of the cosmos. Albert Einstein's theory of general relativity reimagined our universe as a dynamic fabric, a four-dimensional tapestry of spacetime. Massive objects like stars and planets do not pull on things, they simply indent this fabric, and what we perceive as gravity is just matter following the curves and contours of this cosmic landscape. This single, elegant idea solved a puzzle that had troubled astronomers for decades, the slight wobble in Mercury's orbit that Newton's laws could not fully explain. General relativity calculated it perfectly. Then, during a solar eclipse in 1919, Sir Arthur Eddington led an expedition to measure the precise position of stars near the Sun's obscured disk. He found their light was bent, exactly as Einstein had predicted, because their light rays were following the curve in spacetime created by the Sun's mass. This was the moment a new cosmic paradigm was born, but the theory's most stunning implication was its prediction of ultimate darkness. If you compress enough mass into a small enough point, the indentation in spacetime becomes infinitely deep, a bottomless pit from which nothing, not even a beam of light, can ever climb out. Einstein's equations had conjured the black hole. For years, they remained a mathematical phantom, a theoretical possibility many thought might not actually exist in nature. The proof began not with seeing the darkness, but with watching the light dance around it. At the very heart of our Milky Way galaxy, astronomers tracked the orbits of stars whipping around an invisible, monstrously heavy object at impossible speeds. The only thing that could contain such mass in such a small volume was a supermassive black hole. Then, in April of 2019, the Event Horizon Telescope collaboration unveiled the first ever direct image, a fiery ring of light circling the profound shadow of the black hole at the center of galaxy M87. We were no longer just inferring their existence, we were staring into the abyss itself. This theory, over a century old, continues to govern the cosmos on its grandest scales, dictating the motion of galaxies and the fate of the universe itself. How does this curvature of reality itself shape the light from the farthest reaches of the cosmos? A single, powerful whisper from the cosmos arrived on a late summer night in 1977. The Big Ear radio telescope in Ohio was silently listening to the sky when it recorded a signal so extraordinary that it defied all expectation. For 72 seconds, a burst of radio waves, intense and narrowly focused, flooded the receiver. It came from the direction of the constellation Sagittarius, and it precisely matched the profile scientists had theorized for an artificial transmission from another star. It was not random static. It was the kind of signal a civilization might broadcast. When astronomer Jerry Amon saw the alphanumeric sequence printed out on the readout, he was so stunned he circled the string of characters and scrawled one word in the margin: "Wow." That single word gave the signal its famous name and captured the sheer excitement of the moment. This was it, the moment every SETI researcher dreamed of. Yet that powerful whisper was never heard again. Decades of repeated searches using more powerful telescopes have scanned the same patch of sky, listening for a repeat performance. They have found only silence. The very perfection of the signal, its artificial-looking signature, is what makes its disappearance so confounding. If it was a message, why was it sent only once? If it was a natural event, what natural event behaves with such precision and then vanishes without a trace? Proposed explanations, like a signal reflected off a passing comet or some unknown form of interstellar scintillation, have all been debated and found wanting. None fully explain the unique strength and character of that 72-second burst. The wow signal stands as a perfect, frustrating enigma, a siren song from the void that was heard only one time. It embodies the profound challenge of searching for cosmic company. The universe is vast and quiet, and a true signal may be transient, a fleeting flash in the cosmic dark that we must be precisely positioned and incredibly lucky to catch. So what do we do with a mystery that refuses to be solved? The WOW signal remains a beacon of possibility, a reminder that the most important discovery in human history might be a one-time event, a whisper we must be ready to hear. The vast silence beyond Neptune is not truly empty. Far past the Kuiper belt, extending nearly halfway to the next star, a spherical shell of frozen remnants drifts in the deep freeze. This is the Oort Cloud, a theoretical swarm of trillions of icy planetesimals proposed by the Dutch astronomer Jan Oort in 1950. We have never seen it directly, for its objects are too small and faint, lost in the immense dark. We know it must be there because of the comets. Every so often, a long-period comet with an orbit of millions of years streaks through our inner solar system, and tracing its path backward points directly to this distant spherical reservoir. These comets are not random wanderers. They are ancient archives, pristine relics from the solar system's violent birth, and when one is nudged from its frozen slumber, it carries a message from that primordial era. What dislodges them? A gentle gravitational push from a passing star, or the subtle tidal pull of our Milky Way galaxy itself can be enough to send one of these icy bodies on a million-year fall toward the Sun. As a comet approaches the inner solar system, the Sun's heat begins to vaporize its ices, releasing gas and dust that form its spectacular tail. That glowing tail is more than just a cosmic spectacle. It is the comet's history being literally blown into space, a cloud of particles that holds the original ingredients from which our planetary system was built. By analyzing the light from these comas, we can read their composition, finding water ice, complex organic molecules, and amino acids, the very building blocks of life. Each visit from a long-period comet is like receiving a sample return mission from the farthest reaches of our own cosmic backyard, a delivery of raw materials that were present at the very dawn of our Sun. What other secrets about our own origin story are locked within these ancient, icy messengers, waiting for their long journey to bring them into the light? That critical stellar threshold is named for the young physicist who first dared to calculate the ultimate fate of stars. Subrahmanyan Chandrasekhar, just 19 years old during his voyage from India to England in 1930, used his travel time to work through the physics of stellar corpses. He asked a deceptively simple question: what happens when a star's fuel runs out and gravity takes over completely? He realized that a dying star does not just fade away. It fights back with a bizarre quantum force. For a star like our Sun, the final corpse is a white dwarf, an Earth-sized sphere of matter so dense that a single teaspoon would weigh many tons. This incredible density packs electrons into a tiny volume, and these electrons resist being squeezed any further, creating an outward pressure known as electron degeneracy pressure. Chandrasekhar's genius was to calculate the absolute limit of this resistance. He found that if the core of a dying star weighs more than about 1.4 times the mass of our Sun, electron degeneracy pressure will fail. Gravity will always win. This value, the Chandrasekhar limit, became a cosmic dividing line between a quiet fade and a spectacular death. For an isolated star, this limit dictates its fate. A star born with a mass below this threshold will end its days as a stable white dwarf, cooling forever. But a star born heavier will face a far more violent end, collapsing further into a neutron star or a black hole. The true cosmic fireworks begin in binary systems where two stars orbit one another. If one star becomes a white dwarf, it can begin to steal matter from its companion star. This stolen gas piles onto the white dwarf's surface, slowly increasing its mass. For millions of years, this process can continue, inching the white dwarf closer and closer to that fatal limit of 1.4 solar masses. The moment it crosses that threshold, stability shatters. The core can no longer support its own weight. In a fraction of a second, temperatures and pressures soar, triggering runaway nuclear fusion that rips the entire white dwarf apart. There is no collapse, only a titanic thermonuclear explosion, a Type 1, a supernova that can, for a few glorious weeks, outshine an entire galaxy. This precise trigger is what makes these explosions so valuable. Because every Type 1, a supernova, ignites at almost exactly the same mass, they all explode with nearly the same intrinsic brightness. This makes them perfect standard candles, the brilliant mile markers that allowed us to measure the vast distances to far-off galaxies and, in a stunning twist, discover the accelerating expansion of the universe driven by dark energy. How did a theoretical limit for a dead star become one of our most reliable tools for mapping the cosmos? It is a profound connection between the quantum struggle within a stellar corpse and the ultimate fate of everything. Our most precise cosmic measurements are now in direct conflict. This is the Hubble Tension, a stubborn disagreement over the universe's current expansion rate that could signal a crack in our most fundamental model of reality. On one side, we have the pristine early universe. By analyzing the cosmic microwave background with the Planck satellite, scientists can use our standard cosmological model to project forward, predicting a specific, precise value for how fast the universe should be expanding today. This is the universe's own birth certificate, telling us its starting conditions. On the other side, we have the local, modern universe. Teams using the Hubble Space Telescope and other observatories have painstakingly built the cosmic distance ladder, measuring Cepheid variable stars and Type 1, a supernova, in relatively nearby galaxies to get a direct empirical measurement of the current expansion rate. The problem is simple and profound. These two methods, both executed with incredible care and precision, do not agree. The local measurement consistently gives a value that is faster, by a small but significant margin. This is not a simple observational error. This is a discrepancy that has survived a decade of repeated testing and improved data. It suggests that the universe today is expanding faster than our standard model, calibrated on the infant universe, says it should be. So what could be causing this rift? The most exciting possibility is that our model is incomplete. Perhaps there is an ingredient we have not yet accounted for, something that subtly changed the expansion history between then and now. Theorists are exploring fascinating ideas, like a new type of neutrino that adds a bit more radiation to the early cosmos, or a fleeting form of early dark energy that gave the young universe an extra push. These are not wild guesses, but calculated attempts to reconcile the data. Could this persistent tension be the first sign of new physics, a clue pointing toward a deeper theory waiting to be discovered? This conflict is not a failure of science, but its driving engine, pushing astronomers to build even better telescopes and devise even more clever methods to measure the cosmos, hoping that within this disagreement lies our next great leap in understanding. This apparent fine-tuning of the cosmos leads to one of the most profound and unsettling questions in all of science. Why do the fundamental numbers of the universe seem so perfectly set for our existence? The strength of gravity, the mass of an electron, the precise value of the cosmological constant that drives the universe's expansion. If any one of these were altered by even a minuscule fraction, the consequences would be catastrophic for life as we know it. A slightly stronger gravitational constant, and the universe would have collapsed back on itself in a fiery crunch shortly after the Big Bang. A slightly weaker one, and no galaxies or stars would ever have condensed from the primordial gas. The universe would be a cold, dark, and sterile void. This delicate balance is known as the fine-tuning problem, and it demands an explanation. One proposed answer is the anthropic principle. In its simplest, weak form, it states a logical truism. We must find ourselves in a universe capable of supporting conscious, carbon-based life, because we are here to observe it. It is a selection effect. You will never find a fish pondering why it lives in a universe with liquid water, because a fish in a desert does not exist to do the pondering. The more controversial strong form of the principle goes much further, suggesting that the universe must, in some sense, be compelled to have properties that allow life to arise. This idea naturally intersects with one of the most mind-bending concepts in modern physics, the multiverse. Imagine our universe is just one bubble in a vast, bubbling cosmic foam, a near-infinite collection of universes, each with its own random set of physical laws and constants. In most of these universes, the numbers are wrong. They collapse instantly, or they are empty, or they are too chaotic for atoms to form. But in a vanishingly small number of them, the numbers line up by pure chance, and in those rare, life-permitting bubbles, beings emerge who can look around and wonder at their own good fortune. Does this provide a satisfying answer to the mystery of fine-tuning, or is it merely a philosophical cop-out, replacing one mystery with another? The anthropic principle forces us to confront the very nature of scientific explanation itself, challenging us to consider whether the ultimate reason for our reality is necessity, chance, or something beyond our current comprehension. The outer solar system holds a secret written in the paths of icy wanderers. Far beyond Neptune, a group of small, frozen worlds follows orbits that are strangely bunched together, as if an unseen shepherd is guiding their motion through the dark. Their elliptical paths are tilted, clustered in a way that defies the random distribution we would expect from gravity alone. The most compelling explanation for this orbital alignment is the gravitational pull of a hidden giant, a hypothetical world astronomers call Planet 9. This potential planet is no small dwarf. Current models suggest it could be a super-Earth with a mass 5 to 10 times that of our own world, tracing a vast, elliptical path hundreds of times farther from the Sun than Earth. At such a distance, it would take thousands, perhaps even 20,000 years, to complete a single orbit around the Sun, a slow, lonely journey through the frozen fringe of our cosmic neighborhood. We have not seen it yet. Its existence is inferred purely from its ghostly gravitational signature, a modern echo of the mathematical prediction that led to the discovery of Neptune in the 19th century. Back then, astronomers noticed Uranus was being tugged slightly off its predicted course, and they calculated the position of the unseen planet responsible. Today, the clues are not in the drift of a known planet, but in the peculiar clustering of these distant Kuiper belt objects. The hunt for Planet 9 is a monumental challenge. It is incredibly far away, and at that distance it would reflect only the faintest whisper of sunlight, making it a needle in a cosmic haystack of unimaginable scale. Powerful telescopes like Subaru on Mauna Kea are engaged in a meticulous, systematic search, scanning vast swaths of the sky for this elusive point of light. If it exists, Planet 9 is not a newcomer. It is likely a fossil from the solar system's violent youth, a core that formed among the giant planets and was then violently kicked outward into its present distant orbit during a period of gravitational upheaval, a relic of planetary migration frozen in time. Confirming its existence would be a historic discovery, rewriting the map of our own solar system and offering a direct glimpse into the dynamic processes that shaped our planetary family over 4 billion years ago. Will our telescopes finally catch this faint glint in the darkness, revealing a new major world in our own cosmic backyard? these cosmic bullets strike our atmosphere with unimaginable force. An ultra-high energy cosmic ray is a single subatomic particle, a proton or atomic nucleus, carrying the kinetic energy of a professionally thrown baseball, all compressed into a vanishingly small point. This gives it millions of times more energy than anything we can create in the Large Hadron Collider. Such a particle is a direct messenger from the most violent events in the universe, a piece of a cosmic catastrophe hurled across space. But catching these messengers is incredibly difficult because they are exceedingly rare. You would need a detector the size of a city to spot them with any reliability. That is precisely what the Pierre Auger Observatory in Argentina is, an array of over 1,600 water tanks spread across 3,000 square kilometers, alongside telescopes that watch for the faint flashes of ultraviolet light these particles create as they slam into the air. Each detection is a monumental event, a data point from a natural accelerator of almost inconceivable power. Yet this creates a profound puzzle. The universe is not empty. It is filled with the faint afterglow of the Big Bang, the cosmic microwave background. For a proton traveling at near light speed across billions of light years, this background radiation is not a gentle whisper. It is a thick fog. The proton should constantly collide with these microwave photons, losing energy with every interaction. Over immense distances, it should be slowed to a crawl. This means the most energetic cosmic rays we detect cannot have traveled from the far reaches of the cosmos. They must originate from within our own cosmic backyard, from sources no more than a few 100 million light-years away. So we have a relatively small volume of space to search for the most powerful particle accelerators in existence. The hunt narrows to a specific galactic neighborhood, but the identification remains elusive. What cosmic engines reside nearby that are capable of such feats? Suspects include the violent cores of active galaxies, where supermassive black holes eject jets of plasma at near light speed. Gamma-ray bursts, the most energetic explosion since the Big Bang, are another prime candidate. Yet when we look in the direction from which these particles arrive, we often see multiple potential sources, or sometimes nothing obvious at all. Tracing their path is like trying to find a hidden sniper by studying the bullet alone, a bullet that has been bent by magnetic fields on its long journey. The very existence of these particles challenges our understanding of physics and pushes us to discover new, extreme environments where nature can achieve what our finest technology cannot. What ultimate limits does the universe place on energy itself? That faint afterglow of the CMB is not the universe's oldest fossil. An even more ancient relic floods the cosmos, a ghostly sea born in the furnace of the first second. This is the cosmic neutrino background, and it carries a snapshot of reality from a time when the entire universe was less than a single heartbeat old. Just 1 second after the Big Bang, the cosmos was so unimaginably dense and hot that lightweight, elusive particles called neutrinos were constantly being created and destroyed, trapped in a frenzied dance with everything else. But as space expanded at a furious rate, it cooled just enough for this dance to stop. The neutrinos suddenly found themselves unable to interact with the thickening soup of matter and energy. They decoupled, flying free into the expanding void, and have been streaming through everything since, almost entirely undisturbed. These are not the high-energy neutrinos we detect from the Sun or supernova today. These primordial ones have been stretched and cooled by the expanding universe for over 13 billion years, their energy diminished to a whisper so faint it borders on the undetectable. Their existence is a cornerstone prediction of our standard cosmic model, a necessary consequence of the Big Bang narrative. While we have powerful indirect evidence for this background from its subtle gravitational influence on the large-scale structure of the cosmos and the precise pattern of the CMB, a direct detection remains one of the ultimate goals of modern physics. How do you catch a ghost? These neutrinos interact so weakly with normal matter that trillions of them are passing through your body every second without a single collision. Building a detector sensitive enough to feel the faint touch of these primordial particles requires technology at the very edge of the possible, likely involving vast arrays of ultra-pure materials cooled to near absolute zero, listening for the tiniest vibration or flash of light that would signal a capture. Success would be monumental. It would open a window to an epoch we can only theorize about, a time before the CMB, before atoms, even before protons and neutrons had properly formed. We would be witnessing the universe in its absolute infancy, a mere 1 second old. What secrets about the initial conditions of everything are encoded in that silent, ghostly sea? That ghostly sea of primordial neutrinos represents a frontier we are only beginning to approach, but the tools to cross it are already taking shape. We are entering a new golden age of cosmic discovery, built upon the precise maps and profound mysteries our predecessors unveiled. A new generation of observatories, both on the ground and in space, is poised to open windows into the cosmos we have never before possessed, the Vera Sea. Rubin Observatory, with its immense camera that will photograph the entire visible sky every few nights, will create the greatest celestial movie ever made. It will track billions of galaxies, watch for fleeting events, and uncover millions of new solar system objects, all while providing an exquisitely detailed census to further probe the nature of dark energy and dark matter. Following it, the Nancy Grace Roman Space Telescope will function as a wide-eyed Hubble, performing vast surveys to unravel the secrets of dark energy and discover thousands of new exoplanets through its sophisticated microlensing techniques. And then there is LISA, the Laser Interferometer Space Antenna, a revolutionary mission that will place 3 spacecraft in a giant triangle, millions of kilometers apart, to listen for the low-frequency gravitational wave hum of the universe. This will allow us to hear the mergers of supermassive black holes, a deep bass note to the chirps LIGO detected, and potentially hear echoes from the universe's very first seconds. While these machines scan the skies, theoretical physicists are engaged in a parallel quest to reconcile the 2 great pillars of modern physics, general relativity and quantum mechanics. The clash between the cosmic and the quantum becomes unavoidable in the heart of a black hole or at the moment of the Big Bang, where our current laws break down. String theory proposes that the fundamental constituents of reality are not points, but tiny, vibrating strings, whose different harmonies manifest as different particles and forces. Loop quantum gravity, another ambitious framework, suggests that space itself is woven from a fabric of finite, discrete loops. Both theories aim to describe the universe without singularities, painting the Big Bang not as a moment of infinite density, but as a great bounce from a previous cosmic phase, and depicting a black hole's center not as a tear in space-time, but as a transition to something entirely new. The data from our new observatories will test these ideas in ways we can barely foresee, potentially validating one framework and overthrowing another. What happens when we point these immense new eyes at the dark energy that drives our cosmic fate, or when we finally hear the gravitational rumble of the earliest universe? The next chapter of our cosmic story is not waiting to be read. It is waiting to be written by the collision of our boldest theories with the universe's most unexpected answers. From the faint whisper of the Big Bang to the silent pull of dark matter and the relentless push of dark energy, these scientific triumphs weave a breathtaking story of human curiosity. We have transformed from simply watching the stars to actively reading the universe's grand chronicle, using mathematics and technology to translate the language of the cosmos. Each puzzle we solve uncovers a deeper, more profound mystery, fueling an endless and exhilarating cycle of discovery. As we construct ever more powerful observatories and conceive more ambitious theories, we inch closer to comprehending our own humble place within this immense, dynamic tapestry. The next time you stand beneath a dark sky, remember you are looking at a history book written in light, matter, and gravity.